Hi. Hello. Hey there. Yeah, how are you all doing? I know this is kind of like the week where everything starts to ramp up. So, especially starting with this lecture, I really want you to clock in. And if you haven't already, start taking this really seriously because this is where the material starts getting, I'd say probably where it gets really steep. So hang in there. We all know it's challenging, and we're all here to provide support. So today we're going to talk about recursion. And I want to go over some announcements first. Announcements. Hog is due Friday, and if you submit by Thursday, you can get 1 extra credit point. And in particular, a couple notes about that. The final strategy has been released, so you can now test it with the operator. There's some instructions on Piazza. You have to re-download the zip file, but it should be pretty straightforward if you just follow the instructions. Homework 2 is due Friday. And remember that lab checkoffs are happening this week. So you'll have, I think, one more opportunity either in lab on Wednesday or Thursday to check off on a homework or lab that you recently completed. So in that checkoff, we'll just ask you part of essentially just to explain what you did, explain how your code works, explain all that good stuff. So just one or two simple questions about what you did. And if you're confused about anything, come to office hours or sign up for tutoring and mentoring ASAP, because this is the best possible time is right now. Because right now we still have we haven't gone too far into the course, so you can still pick up everything. You're not going to be behind. And at the same time, we haven't really gotten to the really heavy assignments yet, so you still have time to get help. So definitely go to mentoring, office hours, tutoring. And if you want, you can also listen to me blabber about Make Adder, which is this environment diagram that I just want to demo again. The video is on Piazza. And one last announcement, the waterproofing construction in Soda is really loud, especially today, I think. I was in Soda earlier today, and it was really loud, so sorry about that. Especially if you have discussion in 310 or even worse, 320, the rooms will be pretty loud, yeah. All right, so this week we're talking about functions. And the goals for this week are to understand the idea of functional abstraction. So we learned a little bit about that earlier yesterday with higher order functions, and we saw that I could define a single function, like summation, that could do sum of cubes or sum of naturals. And we studied that through, like we said, yesterday we did higher order functions. And today and tomorrow we're doing recursion. And the very end of this week we'll cover some stuff with additional methods of abstraction. All right, so I wanted to go over a little bit of review and introduce the key point of yesterday's lecture. So I think there's one super useful point that Stan brought up here was how to describe functions. This will be really important for recursion. So functions take in some input and compute a returned output. And so the technical terms we use for that are domain, which defines the set of all possible inputs a function may take as arguments, and range, which is the set of all possible output values. And lastly, we also want to define the relationship between the domain and the range, and we call that behavior. So you see that in action with an example like square. Square will take in x, a single real number, and what it'll do is it'll return some kind of non-negative real number. So that additional constraint on non-negative is a useful detail for us to know, because maybe it'll help us identify, hey, we can look for bugs and we know what to test for, essentially. And lastly, we define the behavior, which is essentially what the function actually does. We put it in English and we say it returns the input squared. So kind of the reason why we bring this up is because it ties into that idea of functional abstraction. That I don't think of code in terms of, or I don't think of functions in terms of their code. I instead think of their behavior, what they take in, what they return, and what their job is. So I don't worry about how the function actually computes it. I instead just think of it as a black box. I say, I don't really care how this function works. I can just use it this way because I know the domain, because I know the range, because I know the behavior. All right, so another useful point just to really drive that home. Python, we know, solves problems by evaluating expressions and statements step by step. And so we've seen some examples of that. So we asked you, for example, what would Python display, like we did in quiz 1, to understand how does Python evaluate expressions? What's the order in which things occur? Where do we go next? What's the next step? We also asked you about environment diagrams, which will be, I think, on today's quiz, to visualize the interpreter's process, to see exactly, okay, so I'm going to go here next. When I do this assignment statement, it's going to create a binding or additional steps like that. So in both of these examples, we're seeing how Python computes things step by step. But we're going to do like a little bit of a change here. And for this week, we're talking about functional abstraction. So we think of it in terms of behavior. Square of 2 returns 4. Square of 3 returns 9, and so forth. So the key difference is that we've been doing this up to now, and now we're going to shift more towards that, which is thinking about it in larger terms, more abstractly. All right, so I just wanted to start you off with some an intuitive question to answer, I suppose. Here it is. Suppose you're waiting in line for a concert. It's a really good concert, so you got to go. You can't see the front of the line, but you want to know what your place in line is. And you know if you step out of line, you'll lose your spot. You'll lose your spot, so definitely don't want to do that. What should you do? You can think of this as like a human problem that you have. If I really am literally waiting in line, what should I do? So spend a moment to think about that. Five more seconds. And then go ahead and turn and share with the person next to you what you might do. So you can just put it in English, just say what you want to do. All right, enough talking. I'm going to present to you 2 possible solutions. What's wrong? Can I not? It's not working? Have you guys just been like listening to me shout the whole time? That's terrible. Wait, can everyone hear me right now? Yes, it's good? Okay, I guess it's fine. Okay. Because it's on, I just don't know what's wrong. All right, so I'm going to show you 2 solutions to this problem. The first one is an iterative algorithm. So think back to like your while loops, your for loops. What have you been doing so far in this class, right? What I can do is I can ask my friend to go to the front of the line. This is like initializing or assigning a counter, like I, for example, to be 0. And then I can ask him to count each person, ask them to count each person in line 1 by 1. This is like going through that while loop, I plus equals 1, I plus equals 1. Oops, and then tell me the answer at the end. So return whatever value is at the end. So it's like an iterative version of that. Yeah.
But then your friend loses his place in line.
True, that is a problem. If I ask my friend to do this, he will lose his place. But luckily, I'm there for him, right? And then I could count? Yeah, I guess that would work too. Yeah, another question. Oh, I think that was kind of assumed. Oh, could you give me your names real quick as well? Adam, hi. Greg, hi, thank you. All right, so I'm going to show you the second solution, which is a recursive algorithm. So it's a new key term, recursive. What I might say is, if you are at the front of the line you know you're first, right? If I'm at the front of the line, I know I'm already first. But if I'm not at the front of the line, what I can do is I can ask the person in front of me, what number in line are you? And what that person will do is ask the person in front of them, what number in line are you? And so forth until they hit the front. And that person at the front knows that he's number one, right? So then when the person who's number one turns to the person behind him and says, I'm number one, the second person in line knows that he's number two because he's behind number one, right? And so we can kind of like go all the way to the front, and then all the answers will come back to us, one by one. And that's the idea behind recursion. It's like recursion in a nutshell. There's like an intuition I want you to remember for the rest of this lecture. It would be super useful. We have to go all the way down to the front, and then come all the way back up. All right, so recursive functions. We call a function recursive if the body of that function calls itself either directly or indirectly. So this implies that executing the body of your recursive function may require applying that function multiple times. So here are two examples of recursive structures. One is the Sierpinski triangle. So what you can see here is I have a triangle, and what my algorithm says is, let me pull out the center of that triangle, and then for each of these sub-triangles, let me repeat that process of pulling out the middle. And I can repeat that process infinitely. So this is a structure where I can say, I have this code, or this series of steps, these instructions, and I can say, repeat these instructions, repeat, the same instructions over and over again, however long I want. And that's like another graphical representation. We have Drawing Hands by M.C. Escher, where it's just this interesting picture where you have one hand drawing the other. Kind of the crazy mind-bending idea behind recursion. All right, so we're going to talk about the structure of a recursive problem. I think this is probably one of the most important slides. I think all the slides are important, but this one in particular is maybe perhaps especially important, so take note. There are going to be three parts of a recursive program. The first part is that it has one or more base cases, usually the smallest input. So in the intuitive example, we know that if we're at the front, we're first. So we call that part of the algorithm a base case. And we have, for the second part, one or more ways of reducing the problem and then solving the smaller problem using recursion. So this kind of relates to point 2 of our algorithm, which is to say, ask the person in front, what number in line are you? Because if you think about it, the recursive part is right here. I'm asking the same question, what number in line are you, to someone who's maybe in front of me, right? So they're closer to number 1. So if you relate it to the idea here, the smaller problem is the person in front of me, right? And I'm doing the recursive call when I ask him or her or they, what number in line are you? And the last part is one or more ways of using the solution to solve, solution to each smaller problem to solve the larger problem. So this is where we take the answer that the person in front of us told us, and then we add 1 to it, right? Because we need to add 1 to figure out our position. So there's 3 parts. I have a base case, a way of reducing the problem using some kind of recursive call, and then a way of taking that answer that someone else gave me, and then doing something more with it to compute my own answer. All right, so I wanted to give you a quick demo of how to think recursively. I think this one is a Python tutor. Oops. All right, so here I have a program in Python tutor. It's called factorial. And what it does is it computes the factorial of the number that it takes in. And so the factorial, remember, is defined as like 1 times 2 times 3 times 4, all the way up to the number that you're looking for. So I think we might have already seen an iterative version, but let's take a look at this. So what this code says is I'm defining a function like I would normally. So it's like just looks like any other function. The body looks a little special though. I have an if case, if n equals 0. So you can kind of think of this as like the base case. It's a really small input. And for that base case, I know that the answer is 1. But in the other case, if I don't know how to compute, for example, n equals 1, n equals 2, n equals 3, so forth, what I'll do is I'll do step the second part, which is this recursive smaller problem, right? I'm calling myself, because that's the recursive part, with a smaller input, n minus 1. So if I start with like n being 5, I'll call n minus 1 factorial 4, and then factorial of 3, factorial of 2, factorial of 1 until I hit 0. And then when I hit 0, then I know the answer. And then the last part is combining the answer to the smaller problem with a little bit more, like for example, multiplying by n here to produce my own answer. Because if I'm factorial of 5, I can say, hey, factorial of 4, do your thing. And that'll compute some answer. But that'll be the answer for factorial of 4, right? I'm trying to solve factorial of 5. So I need to multiply 5 with the rest of factorial of 4. So let's take a look at that. So I define factorial. I call factorial on 3. And I check. Is n equal to 0? Nope. So I'll use my else case, which makes a recursive call. So remember to evaluate this, let's kind of step back. To evaluate this expression, right, this is a multiplication between two values, right, two operands. So I evaluate n, I know n is 3. I evaluate this, but this is a call expression. So I need to complete this call expression before I can do the multiplication. So this is where like the ideas from what would Python display, environment diagrams are coming in useful again. So remember how to evaluate call expressions? We have to do this one first. So do that one. Now I'm computing factorial of 2 because that was factorial of n minus 1 or factorial of 2. So I see n is not 0. I'm going to repeat this process again, except this time with n equals 2. So I'm going to call factorial of 1. Factorial of 1 is still not 0. So I'm going to call factorial of 0 now. And now that it finally is 0, I will use the base case, return 1, and then I'm going to go back to the person behind me, the person who asked me factorial of 0. And this person will compute 1 times 1. And that will be the answer for factorial of 1. And then I'll go back to the person behind me and take 2 times factorial of 1, which was 1, right? So the overall answer for factorial of 2 is 2. And factorial of 2 will report back to factorial of 3 and say, I know my answer was 2, so I'll take the part I need to multiply and combine it with your answer to get 6. And that's how we compute the factorial of 3 or 6. Yeah. Was that Arda? Arya, yeah.
So technically, in terms of time of computation, the more that you call onto another function in terms of recursiveness, doesn't it make the computation time longer?
So yeah, so Arya's question was, the larger your input may be, the longer it'll take? Is that kind of good phrasing, or?
In a way, but being calling on so many functions, wouldn't it cause eventually a timeout error?
Yeah, so Arya's question is, if I have to create like so many function calls, right? Look at all these frames. All of these frames are their own function calls. So whenever we call a function, we make a frame, right? So Arya's question was, doesn't this slow things down or cause problems? And yeah, it does. In fact, you might have already seen this before, or you're going to probably about to in your homeworks. If you have a function that calls itself infinitely, what Python will do is it'll cut you off after about 1,000 recursive calls. And it'll say, hey, I think your code is like messed up. And it'll just essentially say, nope, I won't accept it. Yeah, good question.
So if you ran this factorial thing for the number 2000, Python would be like, hey, stop that.
Yeah, it might. Oh, what was your name again?
Braun.
Braun. Awesome, thank you, Braun. Yeah, so Braun's question was, if I ran this with factorial of 2000, yeah, Python might give me an error. Because it'd say, hey, you're opening too many frames. It looks like you're going infinitely long. All right, yes?
Why this function didn't return until n equal to 0?
Good question. I'll hold off on that, and then we'll answer that a little bit later. Is that okay? Yeah. I want to move on. There's also the Piazza live thread, which you can post on as well. All right, so I wanted to go more in depth into that. So here we go. What we just did was, notice that we call the same function back multiple times. And each time, we made a new frame that kept track of different arguments, right? N equals 3, N equals 2, N equals 1, N equals 0. So each frame keeps track of different arguments. And what N evaluates to depends on the current environment. So remember that an environment is a sequence of frames. So for example, I might say my original call to fact of 3, its environment consists of F1, so itself, its own local frame, as well as its parent global. The environment for this fact F2, consists of F2 and global. So they're like two different environments. So what N evaluates to depends on that environment. And lastly, each call to fact solves a simpler problem than the last because it's solving a smaller N. So I started with fact 3, then I looked at fact 2. Each time I got closer and closer to the base case. All right, so if we just rephrase that really quickly. So we have, if you're thinking about, again, going back to that visual of the concert, my question is, what's fact 3? So I ask the next person in front of me, what's fact 2? And what that person will ask is, what's fact 1? And the next person will ask, what's fact 0? And then fact 0 knows that the factorial of 0 is 1. So what fact 0 will do is return that value back up to fact of F3, because now they know the answer. And now that the F3 fact knows its answer, it'll return it back up to F2. F2 will return it back up to F1. And then F1 will return it back up to my global frame, which is where I called fact of 3 from. So it's because I'm making all of these sequences of questions, and those questions are in sequence answered, we get a way of solving this problem using recursion. All right, so I wanted to also introduce you to two different ways of viewing recursion. This is pretty useful. So let's see, first of all, we have recursive leap of faith. So this is an idea that relies upon functional abstraction. And so our question we want to answer is factorial correct? Right? How do we know that our code written over here, how do we know that it works? Well, what we can do is we can verify that the base cases work. So the base case n equals 0, we know that factorial of 0 is just going to give us 1. That's like a given fact. So check that they're correct and that they're exhaustive. So here we just need a single base case, but sometimes we might need more than one base case. Now, for the second part, we need to harness the power of functional abstraction. So this is where we assume that factorial of n minus 1 is correct. So what the functional abstraction says is, if I treat this like a black box, if I just assume that factorial takes in some number and returns some number out, and its behavior being that it'll give me the factorial of its input, then if I assume that that's all correct, then what I can do is I can verify that. Knowing that that's correct, if I know the factorial of 2 is, for example, 2, and if I'm trying to compute the factorial of 3, all I need to do is multiply 3 by factorial of 2 to give me 6. Yeah, so John B.
Can you quickly recap, what does it mean for base case to be exhaustive?
Yeah, so John B's question was, what does it mean for a base case to be exhaustive? And so in this case, exhaustive here just means that it covers all the possible conditions where you might have to get to this base case. Like the problem that we saw earlier in the concert was that you only have like a single line, right? You just have one line. And you're going to the front of that line and there's like no one else, like there's not gonna be like a line that diverges. But in the next lecture, we'll see that there might be, for example, concert lines that diverge. And there might be multiple endpoints. So how do you handle those multiple endpoints? You need multiple base cases. Good question. So that's like a bit of a sneak peek. All right, so again, functional abstraction. We just don't worry that that factorial is recursive and just assume that factorial gets the job done. So we don't worry about the fact that it's recursive or any funny business like that. Yeah, question?
If you're calling it a leap of faith, doesn't mean it sometimes doesn't make the
Yeah, so what's your name again?
Martin?
Yeah, Martin asked if what's up with leap of faith? Yeah, sometimes if your code isn't correct or there are maybe problems with the way you combine information or if your base cases are like a little off, then that leap of faith might not work. But the idea is that if you have the correct base cases and if you combine the information in the right way, if you combine your recursive call with your additional information, like multiplying by n, If you have the correct combination of base cases, part 2 and part 3, then that leap of faith should hold. But if any of those 3 parts are out of sync, then they'll cause a program to break. Exactly. Cool. So I want to dive more into that. So what we can do is we can look at how we computed factorial of 3. So as an example, we saw factorial of 3 required computing factorial of 2, required computing factorial of 1, required computing factorial of 0. And so this is how we see that we can verify the correctness of recursive functions. We can kind of start at the base case because we know the calls will all go to the base case. We go all the way to the base case, right? So if we know the base case will work, then if we examine the case that's one step away from base case, when factorial of 1 was called, we check that that works. We check that factorial of 2 works. We check that factorial of 3 works. And if everything works so far, and if you can extrapolate out to the future, that factorial of anything, then you can be pretty convinced that it'll work. But this kind of brings us on to like another way of thinking about recursion, which I don't think has been taught very much. So this is like a different technique. So whereas the first one was a view called recursion using leap of faith, this one is recursion by enumeration, which is a neat technique that I think is super useful if you don't know how to start. All right, so here's another way of defining factorial. And in fact, I think it'll be more fun if we pull up the editor. So let me do that. So I'm going to do, oh my bad, is I'll have factorial of n. And what I can say is, if n is 0 or if n is 1, I know that in both of those cases, I returned 1, right? Because factorial of 0 is 1, factorial of 1 is 1 times 1. So I just return 1. Otherwise, if n is 2, what I can do is I can say 2 times 1, because I know that's what factorial does. If n is 3, I could say 3 times 2 times 1. If n is 4, I could say 4 times 3 times 2 times 1. N is 5, I could say 5 times 4 times 3 times 2 times 1. And this is getting painful. So I don't want to keep on enumerating all the cases. Like this code could work. If I just listed out every single possible case, I could get this to work. But an easier way might be to do this. 6 times factorial of 5. And then I can see generally that this becomes n times factorial of n minus 1. So I kind of want to point it out where this came from. This is the idea of functional abstraction again. Is we see that I just want to do 6 times 5 times 4 times 3 times 2 times 1. But I don't want to have to write out 5 times 4 times 3 times 2 times 1. So what I can do is I can say, hey, where else in my code have I done 5 times 4 times 3 times 2 times 1? Let me call that right here. Let me substitute that out. And then using this way, we can find a pattern. So we're still answering the same question. But this time, if we list out all the cases, identify the pattern, and then simplify repeated code with recursive calls, this is kind of like a way that will essentially always work, or at least it always worked when I took 61A, to solve recursive problems. So here's like the generalization. If I see from this pattern, if n was 6, I could substitute that with n, and this was n minus 1. So I just want to figure out how do I manipulate these numbers or my inputs so that I get the right values to go in there. And kind of the key point behind this was that I kind of wanted to show you that recursive calls aren't any special. We follow the same rules for evaluating call expressions, and there's like no special handling for recursive calls. We just do operator, operands, and then apply. Okay. I'm going to give you a challenge. Do this. Write some code. Try to solve this problem. So what COUNTUP will do is print the numbers from 1 to your input, each one on a new line. So we know print, if you just say print of 1, it'll give me 1 on its own line. If I said print of 2, it'd give me 2 on its own line. So try to use either the leap of faith or the recursion by enumeration to help us solve this problem. So spend a moment, think about it on your own. Then I'll let you break up into partners and talk about it together. All right, so I was looking up Josh Hugg's slides today, and there are 3 good ways of doing this problem. The first way is you can do it on paper, which is the best possible way. If you have a piece of paper, take it out now. Do it. Take it out. Take it out. Take it out. I know your names. Take it out. Take out a piece of paper and write it down there. That's the best possible way. If you really don't have a piece of paper, a laptop is okay. The worst way is just thinking about it in your head. But really the best way is using a piece of paper, because then you can really say, hey, this is what I was really thinking of. And you can't like kind of cheat yourself and say, hey, I was kind of thinking like that. Or you can't like rely on the computer and say, okay, I can just edit this now that I see the output. So really try to predict what will happen with your code when you write it out on paper. Is it working?
Not working at all.
I think was it working?
I think it is working. It's kind of
Just
hard to
really
tell.
low.
It's kind of hard to tell. But if you tap it and it makes sound, then
Oh.
it should work, right?
Maybe.
Because I feel like this mic has to like yell into it.
Yeah, I think it has to be, you have to get the right direction. All right, so now that you've had a chance to think about it on your own, turn to the person next to you and, okay, don't shout your answer, but like talk to them about it. You want to go walk around checking people? Or... All right, let's try this out. So I'm going to do a quick coding demo to show you how recursion by enumeration works in this example. So we saw that recursion by enumeration. Recursion by enumeration. So here we know we define a function called countup that takes in an n. We know that the way it works is that it will recursively print up to n. And as an example, recursion by enumeration, it's really important that you have examples in mind. So think about the smallest possible inputs I could give to this program. I think countup of 0 is pretty small. And so maybe countup of 0, what should print out? It's kind of a hard, kind of like a tricky question. Nothing, yeah, because the way countup worked in the slides was that it only went up to 1. So if I ask it to count up to 0, I guess nothing will happen. So we need countup of 0 to do nothing, countup of 1 to print 1, countup of 2 to print 1, 2, countup of 3 to print 1, 2, 3, and so forth. Right? And what I've just written right up here is what's called a doc test. So what you can actually do is write your own tests, like kind of how OK provides tests for you. You can write your own tests just like that. And you can run these tests by saying python3-m doc test and your file name. And you'll see that I'm failing all of my tests because I haven't written any code at all, right? It's a completely blank function, so of course I'm failing all of my tests. But let's say, what if I try to solve countup of 0? I think countup of 0 is already right because it should be blank, right? Well, if we try to solve countup of 1, n is 1, maybe what we can do is we can print 1. And let's check that that works now. So hopefully, we failed 3 of 4 because countup of 0 passed, right? So now that we try to run it again, maybe we'll fail 2 out of 4. Progress. 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 And we just keep on doing this. This is the idea behind recursion by enumeration. We think of some cases and we try to solve each case one by one. Even if it's completely dumb, even if it looks like this. I've solved it, right? I should get 3 out of 4. Yes, 1 out of 4 failed. I'm a god. And we keep on doing that for n equals 3 as well. Print 1, print 2, print 3. And now I've passed all my tests. Yes. All right, just one problem with this. It's not recursive, right? Let's make it recursive. Where's the pattern? Let's look between 2 and 3, right? I'm using print 1, print 2. Print 1, print 2, right here, right? So let's reuse that. What I can do is I want to reach that n equals 2 case. So this code right here for n equals 2, it's hidden inside of count up. So I need to call count up with 2. And hopefully it still passed my test. Yes, it still passed the test. So that means the code still works. And in fact, if we try it out ourselves by loading it in the interpreter with -i, what I'll get is, let me make some space, or that was not making space. My bad, let me make some actual space. All right, so if we actually test it out now, we can do count up of 1, looks good, 2, looks good, count up of 3, awesome. So recursion by enumeration seems to be working so far. And what we can do is we can try to generalize this now. Else, let's try to find the pattern. If n is 3, then I can call count up of, I guess, n minus 1, right? Because that's how you get 2. And then I can print n. And now I have a more general version of this last case. So now that you've done the 3 steps, or 2 of the 3 steps. You've done listing out the cases, you've found the pattern, you've found a more general version of that pattern, and last part is just cleaning up your code. So here we have some repeated code, right? Because this case is now handled by the general case. And this one too, I think. Because imagine that we didn't have this code for n equals 2. If I'm just using this case, I'll call count up of 1, which prints 1. And then it says print 2 after that. So I don't need this code either. So this is one way to write count up. And hopefully, we try our code again using the doc test, which is you type that, python3-m doc test, and put in your file name. Oh gosh. Oh! What happened? Maximum recursion depth exceeded. Oh no! What do we do? What happened? Yeah. The 0 case? 0 case, right? So we have this test for 0. What happens if our count up, what happens if we call count up with 0 here? Because it'll check, right? It'll check if, is it 0? No. And then also use the else case, right? And the else case says, call -1. And then -1 is not 1, so it'll call -2, -3, -4, -5, -6, forever and ever and ever, until Python gives up and says, runtime error, maximum recursion depth exceeded in comparison. So that's why that failed. So we need to fix that. This is a problem with our base case. Because we want it to work correctly on count up of 0, but our base case is defined for count up of 1. Right? So we really need a way to account for count up of 0. Yeah, Varan, go ahead.
For count up of 0, it should just return nothing, right?
Mm-hmm.
So couldn't we just make it so that else doesn't happen?
Yeah, we need to think of a way we can get it so that count up of 0 returns nothing.
So we can take that else and make it an elif for count up of 0.
Yeah, maybe we can handle it by making an elif. Let's check if that works. Elif n is greater than 0. And then if it actually, so if it's not in either of those 2 cases, right? What it'll do is it has to be 0 or less. So then in that case, I just do nothing. I can just say return. All right, so it passes again. Yeah, that's one way of fixing it. Adam, go ahead.
Did you even need to add the elf at the end? Could you have left it as just the elf and then it wouldn't return anything because it just finished going through the entire code?
Yeah, so Adam is hinting that there might be a more elegant way or shorter way to write this code. And in fact, I think I have that on my next slide. So let's take a look. Here is the code. So that's count up. And what I can say is, if n is greater than or equal to 1, let's call count up of n minus 1. Otherwise, and then print n after that. And that's it. This is all the code. Notice that there's an implicit base case. So remember, we were trying to deal with that condition if I'm 0, right? Because I know if I'm 0, I want to do nothing. So what happens if I call count up of 0 on this code? Well, I'll go down to the body of the function. I'll say, is n 0, right? Is 0 greater than or equal to 1? No, that's not true. So I skip this block, and I go to the bottom, which says there's nothing else here. So I return none, and I'm done with 0. So this handles the 0 case by saying if I'm less than 1, I do nothing. And for every other number, if I'm 1, for example, I'll call 0. I'll call countup of 0. But we know countup of 0 does nothing, which is fine. And then I print 1. So that handles countup of 1 as well. And then from there, we can kind of see countup of 2, we'll call countup of 1, and then print 2 after that. So it all kind of works out. Questions about count up? Yeah, go for it.
So you don't need to return anything when you're printing because even like passive
Yeah, great question. What was your name?
Mustafa?
Mustafa? Yeah, so Mustafa asked, we don't need to return anything and it'll still like handle itself? Yeah, so the way recursion works is that I'm still calling this function, right? I'm calling count up n minus 1, and it'll do its thing. So let's say I'm trying to solve countup of 1, right? So I'm going to call countup of 0. And what countup of 0 will do is say I'm not here, so I go down here, right? And I say there's nothing else, so I return none. So even if there's no return statement, it'll return none, right? And that return none brings you back to the countup of 1. So the important part I think that you want to see in this code here is that when I call countup of 1, if I am countup of 1, I'm going to call countup of 0. It's going to do its thing, which is nothing. And then when countup of 0 is done, I come back to countup of 1 and compute the next line. So there's like more work that might need to be done. So that's like the important part as well. All right, Adam.
Can you do this entire function with a for loop, like for x in range n, just print x plus 1?
Yeah, so Adam's suggesting that we could use an iterative solution to this as well, and that's totally possible. You can use the for loop. Okay, cool. So I kind of wanted to go through that a little bit more. So I want to contrast like the two methods that we saw earlier, leap of faith and enumeration. So I showed you a demo using enumeration, but let's talk about leap of faith and how you might solve this problem using that as well. So the important thing is that for both of these problems, you have to think about the small cases first. So in leap of faith, we jump straight into what's called the base case of the recursive program. And we think about what's the smallest possible input. So I might think, hey, maybe if n is equal to 1 or if n is less than 1, maybe I need to handle that case. Then after that, I would start thinking about how I might need to reduce the problem. What kind of recursive call needs to be made? And so I know to print the number before us, I can rely on the fact that I defined count up to be a function that counts from 1 to the number that you give it. So if I just call count up with n minus 1, I'll get the desired result of like, for example, if I call count up of 4, I'll get 1, 2, 3, 4. So this is where you do that leap of faith part where you assume that count up of n minus 1 works. And then finally, you solve the larger problem, which is introducing printing ourselves, because that's how we actually get to count up of 5, for example. So I need to print n for myself. This is kind of like the thought process I would go through when I'm thinking about this. But I think it is definitely like a little bit harder to think abstractly and to really trust why this all works. So we'll have like another slide to talk about that as well. Then you saw me do enumeration on the screen. What we did was we listed out the cases, right? So if I said if n was 1, print 1, if n is 2, print 1, then print 2. And then I tried to identify the patterns. We found that n equals 2 helps solve n equals 3, because we'd have that repeated code, print 1, print 2. And then we just simplified our code using recursion. So if n was 3, I went ahead and substituted print 1, print 2 with countup of 2. All right. Okay. Any questions about this material so far? We'll move on. All good? Yeah.
So which way do you use more often, or which one is more helpful?
Yeah, great question. What's your name?
Yay.
Yay. Yeah, so cool name. Kanye, yeah. Okay, so the question was, which one do I use more often? And I think when I was taking class, I definitely found this technique to be a lot more useful in enumeration. I found enumeration to be a lot more useful when I was writing code. But now that I've become a lot more comfortable with recursion, I actually rely more on this now because I can see the steps ahead. I can like visualize all the steps ahead, and I kind of understand both like the abstract view of this is what the program does, as well as the steps view. This is what the program's executing on each line. So kind of like the reason why we teach all of this is because we want you to see programs from both worlds. We want you to see programs as an abstract black box function, and we also want you to see programs as something that is evaluated by Python. So I think at this point, when I was in the course, this is more comfortable to me, so I like using this more. But if this works for you, go for it. I like both of these techniques. Yeah, any other questions? You can ask personal questions too. Why was that so funny? All right. All right, so I wanted to take a break now because we're a little ahead on time. So go ahead and have a party time. I'll put some music on.
It's a way to circumvent.
I think it's useful. I don't care.
I don't care. Okay.
What's good? What's good? Oh.
Might want to tell them that enumeration might not work really well with getting trees.
Yeah.
Just like for now, it's like a good step, but later in the course we'll have to.
I think it's useful for Hanoi though. I think that's why I think it's so useful.
Yeah, I think it's really good. So yeah, just let them know. I mean,
Yeah.
I'm gonna be teaching trees, I think, so I'll let them know
So
that.
I'm doing tree recursion tomorrow.
Yeah,
We're doing trees.
You have to do actual trees and like the beautiful trees.
All right, let's come back together. That was a good break. And lastly, I want to talk a little bit more about what Adam kind of pointed out earlier with the for loop, was that there's some kind of relationship between iteration and recursion, or at least so far with what we've seen. So iteration is actually a special case of recursion. So whenever you use that while loop or whenever you use that for loop, what you're doing is actually like a special kind of recursion. And the thing to know is that converting iteration to recursion is formulaic, and I'll show you how that can be done. And converting recursion to iteration can be more tricky, and that'll be kind of like a topic for later. So let me show you two versions of factorial. So here's an iterative version. I call it factiter. What it does is it starts off, takes in some n. So n tells us how far we have to go, to which number to compute up to. And inside, we define like our usual loop kind of thing where we say, I need to keep track of a total. I need to know where I am up to that n, right? So what my total will do is keep track of the final value, and I'll have a k to keep track of where I am in the sequence for factorial. So if I say while k is less than or equal to n, I'll compute total comma k equals total times k and k plus 1. So again, this is a double assignment. Total times k will become the new total. So that'll be like essentially taking 1 and then 1 times 2. and then taking that 1 times 2 and multiplying by 3. K will become k plus 1, so it'll just increment our counter, so we'll know we're getting closer to n. In the very end, we return the total. So if we take a look at the recursive version, which we've seen quite a bit today, we have a function called fact. If n is 0, we return 1. Otherwise, we return n times factorial of n minus 1. So if we think about the way this is formulated, the way fact iter works is that it starts computing the sum, or the product, starting from 1. Right? It says start from 1, go 1 times 2 times 3 times 4 times 5, however many you need for factorial. What the recursive version does is it starts from the big number, for example, factorial of 5. And when it does it, makes recursive calls until it hits factorial of 1. But then when it computes factorial of 0, for example, factorial of 0 will return back to factorial of 1 and say 1 times 1. And then factorial of 1 will return back to factorial of 2 and say 2 times 1. And then we'll take factorial of 3, 3 times 2 times 1, and we're starting to see that same sequence form again. Except whereas iteration did it from the beginning, I said 1 times 2 times 3, factorial has to go down the stack, has to go down and make all those calls. And then when it's finishing each call, that's when it performs the multiplication. So we're still performing the same sequence of operations. It just does it in a slightly interesting order because we have to go all the way down to the base case and then come back up. Whereas iteration, we start at the base case and kind of just move on from there. There are a couple other differences I want you to take note. So we can think of the definition. If you're really into math and you can read this, what that says is n factorial is the product of all k, where k starts from 1 and goes to n. So it's like saying 1 times 2 times 3 all the way up to k. That's how we define factorial for the iterative version. And we define factorial for the recursive version using cases. So we can say n factorial. We use the case that n, we return 1 if it's the case that n is 0. Otherwise, we return n times n minus 1 factorial. So it's like an equivalent definition. But the important part, I think, for us is here. We keep track of different bits of information. In the iterative version, we need many more pieces of information. And this will be relevant for your homework as well, when you're thinking about how I might have to go between these two versions. In the iterative version, I need to keep track of more names. Whereas in the recursive version, I don't need as many names. Right? So how does it keep track of that same information? This is like a really big problem. I think it'll be useful for ping pong as a hint. So when you're trying to write ping pong, for example, you'll notice that you're trying to keep track of more information than your function can take in. Because remember from earlier when we were looking at those environment diagrams, right? We saw that. Let me go back a couple slides. Let's see. Here we go. Let's go back to this one. So remember that different frames keep track of the different arguments in each call. That's how recursion solves that problem between the iterative version having 4 names and the recursive version only having 2 names. Because each frame kind of keeps track of its own information. That's kind of like an interesting point for us, because if we look at what we need to do, so we have 4 names here and 2 names in the recursive version. It's an interesting point for us, because these same totals have to show up in, like, for example, the return value. This is like implicitly the total, right? But you'll see an example of like where I need to keep track of more information than what is just simply given. So in ping pong, where you keep track of more information than what is given, the key technique is to provide more names. And the way we do that with recursive programs is by giving it more parameters. So remember that, again, I really want to repeat this because this is a really important point. Sorry about this. So different frames keep track of different information, right? If I want to keep track of the same information, I'll need to add more arguments, more parameters. That's a useful bit of, it's a useful hint, so make sure you remember that. All right. Lastly, let's go into the summary, and then at the end, I'll show you another example of a recursive program. So recursive functions call themselves either directly or indirectly in the function body. So the motivation for this is to break down the problem into smaller, easier to solve problems. So we saw that we could solve factorial of 2 using factorial of 1, using factorial of 0. And that might sometimes be easier to imagine. And in environment diagrams, we keep, each call creates its own frame and keeps track of its own argument values. Recursive functions have the 3 parts we want to think about. They have base cases, which evaluate without relying on calls to itself, and recursive cases, which do. So what I want you to remember when writing recursive programs is to think about those 3 parts. I need a base case, or more than one base case. I need a way to solve a smaller problem using a recursive call. And I need a way to combine the answer to that smaller problem with some more information, with some more data to solve my own problem, right? So we're thinking back to the concert. The base case was, if you're at the front, you're first. My recursive call was I asked the person in front of me, what number in line are you? And then my last step was adding 1 to the person who gave me the answer. And then the last hint is to use both leap of faith and enumeration to help us solve problems. So are there any questions about recursion at all before I show you the last demo and then we'll be done? Yeah, go for it. Can you stand up and shout? It's a little far, yeah.
Okay. What you were saying earlier is different frames keep track of different information.
Yes.
So if you want to add information, you add functions and arguments. Is that what you're saying? Or?
Right. So notice that, for example, let's say I wanted to keep track of 2 names. Like I want to keep track of 2 numbers that are different from each other. What I would need to do is, because each frame here can only see itself, F4 for example, and global. You can't see F3. You can't see F2. You can't see F1, right? If you want to know of some other number, you need to keep track of it in here. And the way to do that in recursive programs is by adding additional parameters. So instead of it being just fact n, I might say fact of n and k. It's kind of hard to see how that applies in this example, but in the future, for ping pong in particular, you'll need this. Does that address your question? Or awesome. What's your name, by the way? Mina, thank you. All right. Let me show you the last demo real quick. And demo time. Okay. So I'm going to just show you how to write a simple program that kind of combines some of the different ideas we've been learning in this class. All right. So I'm going to show you. Let's try to define a program that can sum digits. So I'm going to call this program sum digits. It takes in some number n. And what it'll do is return the sum of the digits of positive integer n. So for example, I might say sum digits of 9 is just 9. Sum digits of 18117, that's 1 plus 8, 9, plus 1, 10, plus 1, 11, plus 7, 18. So those are like 2 simple cases you can just come up with and just add the numbers, add the digits to get your solution. So the question is, what do we do here? We''ve seen something similar where we did it using iteration, I think, but let's try to do it recursively this time. So the way that we solve these problems for both enumeration, leap of faith and enumeration, for both of these strategies, we always have to think about what are the smallest cases, right? What if, say, I have a number with only 1 digit? That's a pretty small case. Or a number with 0 digits. So try to think of like those 2 cases first. So we can handle that by saying, if n is less than 10, let's just assume we're only working with positive numbers here, or non-negative numbers. I might say, if n is less than 10, then it's like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And if we ignore the negatives, so that would just be a single digit. And we know the sum of a single digit number. I think this is like a kind of the tricky part of the base case is trying to think about it without looking at everything else. So we know that the sum of a single digit would just be that digit itself, right? So if I give you the number 9, the sum of its digits is just 9. So you can get all of this information just by looking at that first example that we came up with. So I really, really want to encourage you to think about it in terms of examples and try to solve it in terms of those examples. So I made an example for count above 9, and I solved it by writing this general base case. And then we can try to come up with a recursive scenario for where I can solve maybe a 2-digit number using the fact that I know how to solve it for 1 digits. Right? And we know with numbers, I can split up numbers using the modulo and division operators if I just modulo by 10 or floor divide by 10. So remember that we can split numbers with floor dividing by 10 and modulo by 10. So what we can do is we can say, for example, if I want to get just the last digit of a number, let's say we're looking at a new case, for example, some digits of 18. If I want to just get that last digit of that number, I can do n mod 10 to give me the last digit. I can do n floor divided by 10 to give me all but the last. That's the way I want you to think about these two calls to modulo and floor divide. So using those two tools, what I can do to solve some digits of 18, which is just going to be 9, is I can take, for example, the last digit. So I can return the last digit, which will give me 8, right? I'll give you the number 8. And I can add it to the sum digits of the rest. So sum digits of the rest will say the rest of that number is only the 1. And we know when we call sum digits with 1, we go to the base case and return 1. So we get 1 plus 8 is 9. And the way to keep on verifying this is one way is you guys keep on coming up with more examples. Let's try it with 18117. What we'll do is we will look at the 7 first. So we evaluate 7, and then we add it with some digits of 1811. And then what that call will do is look at the 1 and split up 181. What that call will do is look at the next one and give you 18. What that call will do is look at the 8 and give you 1. And the very last one, the very first one that actually finishes, is some digits of 1. So we go some digits of 1, and then adding that to 8, adding that to 1, adding that to 1, adding that to 7. And then we ultimately solve the problem. Yeah, so I just double check that this code works using our test. Python 3-m.s demo. Awesome, so passed all the tests, didn't say anything. Any questions about this material or anything at all? Joanne, go ahead. Oh, this method? This method is, what would I call this? What would I call this? Or, yeah, so Joanne's question is, what would I call what I just did right up here? I'd say enumeration would be just solve the cases, just solve like strictly for those cases. Like I would say enumeration would be like if n is less than 10, if n is less than 100, if n is less than 1,000, solve all those cases individually, then squash them together. This is more of, I think, leap of faith, where I assume that some digits of n divided by 10 just works, and then I can split it up to solving some digits of the last one and some of the rest. All right, if you have any other questions, feel free to come up front. Otherwise, you're all dismissed. Thank you so much, and please be kind to your TAs. They'll be working under distress with the construction.
If we turn in the project by Thursday night, then get us credit. I didn't check how far. What's the percentage rate we need this time? Is it above 70%?
73.5. Yeah, and we gave you the full auditor. So you can just run it however much you want.
So just very quick, one quick question. So you said in the slides that iteration is a specific case for conversion. I was wondering, is that a mathematically accurate statement? Is there a book or a paper on it that I could read?
I think it is. I'm not sure. I'd have to look up some resources, but I can get back to you on that. Maybe I can research some, and you can research some too. Yeah, what's your name?
Kasra.
Kasra?
Kasra.
Kasra. Okay. Yeah, let's talk about this later then. Okay, let me take note of that. Yeah, let me remember that. Hi.
Yes, I'm just wondering if
Chris?
Bibo.
Bibo.
Yeah, I don't
Hi.
think I've talked to you.
Yeah.
Here's the thing, this is the second week here, and then I'm also finishing up my finals in a community college. I have 3 finals this week. It's getting kind of crazy. I'm just wondering if I can get a letter, a deadline for the housing project to Sunday or something. Because right now I'm in the middle of 3 my finals, and I don't have that much time until Friday. So,
Okay, so when do your finals finish? We can try to work something out.
Okay.
Yeah, I think that's fair.
Okay.
Okay. Do you want to email us?
Yeah,
You can email
I'll send you an
CS618.
Okay.
CS618 at Berkeley.
Okay, thank you.
Okay. So first off, what happened to your airline tabs, the arrows in Vim?
Oh wait, what happened to mine?
Yeah, because you're using airline, but you don't have the arrow thing.
Oh, I think it's because my font. I'm just doing it over SSH, so I don't think I have the font set up. I'm using Chrome OS, so I don't have airline fonts.
Wait. With Chrome OS, aren't you using it rooted? Are you using it rooted?
No. I only use the shell. I only use the
so
shell.
you're not using unlocked.
No, not dev mode. Yeah.
Okay.
Yeah.
Because that's what I thought you were doing. So you're just syncing into your home or something. Your
Yeah.
desktop? Also, what switches?
These are Toprate.
Toprate?
Yeah.
Never heard of that.
Never heard of it? I guess that's actually. I think a lot of people I've talked to just don't know about it.
They're very quiet.
Really? These are. I think they're mid-level sound. Yeah.
I've got browns and blues at home, so yeah, my blues are.
Oh, are you the person who said you spent thousands of dollars on keyboards? Or someone else is like us then. We spent they said on the pre-semester survey I spent thousands of dollars on keyboards. So.
All right, I'll let you guys.
All right. See ya. Greg, right? Yeah. See ya.
So I just changed courses this week. I was in CS9 before.
Yeah.
So what should I do about the work that I missed last week? Should I just try to finish it?
Yeah. Yeah, for sure.
Okay. All right. Thanks.
Yeah, and then we email CS618 at berkeley.edu. We can try to work something out for figuring out how the extensions will work.
Okay. All right.
Yeah.
So looking at the previous midterm test, there's one environment diagram that I don't get. How do you get
Oh, do you want to work on this? I guess do you want to work on this outside? Yeah, because I think we have to leave right now. But yeah, let's work on it outside. As long as you have the time. Yeah. Okay.
So the recursive function is just a special kind of higher order function.
Is it higher order? Let's see. Not really.
Oh, not really, because